The presentation I've prepared is based on the work of our Research and Development Initiative. The use of meta-analysis in social sciences, particularly education. Education is my background, so lots of my examples will be drawn from that field. But it was very much a collaborative project working with a number of colleagues and universities, and we designed materials to help people's sort of understanding and engagement at different levels. I think it's particularly important that we start to support all researchers from sort of master's and doctoral level students and above in at least being able to critique meta-analysis, and that's one of the key things I'd like to persuade you of today. And then of course I think there's another dimension that I think there's some value in actually doing and undertaking meta-analyses, and that's kind of the different levels of training that you see on the slide. But we had a real commitment to engaging with doctoral students, and are very grateful for the support of BERA in that, in letting us run some sessions at their annual conference for students. Okay, what is meta-analysis? I've started off at a very basic level, and the key idea is that we should be able to combine results from quantitative studies so that we can accumulate evidence. A notorious problem in particularly educational research, but social science research more generally. Of course, that raises a whole host of issues that I'll need to touch on as we go through the presentation. I think it's also a way of comparing the results of similar studies. So we start, if you like, for me, it's part of drawing the map of evidence. So that's another sort of metaphor I'd like to throw out. And then my particular interest is in how we can investigate patterns of association in research over time. Can we accumulate a richer understanding by aggregating quantitative findings from different studies? And again, the metaphor that I use is, if you think of it as being a way of surveying research, effectively you run a questionnaire in which your subjects are the research studies, and then you look at the patterns of data that emerge from that. So at that level, although meta-analysis is often of randomized controlled trials which are trying to identify causality, meta-analysis is fundamentally correlational, so any patterns that result may be as a result of the associations in that data rather than necessarily indicating causal links. I kind of need to get that out of the way because I think that is a key issue. If you want to compare data across different studies and accumulate evidence, you need to be able to convert the data in them into some sort of common metric, some way of equating quantitative values across studies. And in meta-analysis, we use effect size as that common measure. And I'll spend a little bit of time sort of explaining that. So I hope we'll get a picture of what that is. I'm not assuming any statistical knowledge. Some of you may well know more about effect size than I do, but I thought that was a good place to start. And then I'd like to talk a little bit about the limitations of meta-analysis and its potential. So brief, if you like, for what I'm going to try and cover. Effect size, as I've just mentioned, is a way of trying to standardize difference. So suppose there have been a number of studies of ways to improve reading in school, and they've all used different tests. And you can see that they've all had a range of effects, some very positive, some not so positive, but you're not quite sure what the overall picture is. The idea of meta-analysis is that you convert all of those scores into a common metric so you can compare the different interventions with each other. I'm going to focus today mainly on talking about evidence from experimental studies, because again in education that's a particular important dimension in terms of intervention research. But you'll see meta-analyses done with other data. In medicine you get a lot of odds ratio work. What's the best way to describe that? I suppose whether patients get better or not, or whether they die or not. It's binary outcomes. So you can look at proportions and meta-analyze those. You'll find a lot of meta-analyses of correlational research. So suppose there have been lots of studies of gender difference in mathematics, looking at the correlations between boys and girls' performance and finding differences, and they've been done over time. You could combine those studies to identify what the overall effect is to be more secure in your understanding of those gender differences. Or it may be that you want to look at the impact of different interventions. So I mentioned before reading interventions, different ways of teaching phonics. Say the last government was obsessed with phonics. I'm not sure this current one is going to be much different. But there's certainly evidence out there that it's an effective way to improve reading. But is it more effective than other means? Is it more effective than involving parents or developing homeschoolings? Is it more important than methods that focus on developing understanding rather than simply decoding text? We might want to be able to compare the results of different interventions to improve reading skills and be able to read across those different fields. And that's partly what an effect size does. And for those interested at a more technical level, the way you calculate it is very straightforward. You look at the difference between the intervention and control group and you divide it by the standard deviation. So it's a kind of ratio measure of difference relative to the dispersion of scores. I'm going to try and sort of build a picture, if you like, of what an effect size feels like, because that's a kind of very cognitive description of effect size. I'll try and sort of show the way I understand it, and I think of it as being to do with normal distributions, and that's my symbol for a normal distribution as I wave my arms in the air, and I think of it to be the extent to which those normal distributions shift one way or the other, and it's the amount that they shift that is the metric of effect size. So this would be a fairly small effect size, 0.2. Again, this is just me thinking about how we can visualize what that might be. This would be, I suppose, from correlational data. But if you think of the height difference between 15 and 16-year-old girls, you wouldn't really want to place a lot of money and bet who was older by who was taller at that age. They'd be pretty hard to tell apart. And as you can see from the distribution on the screen, there's not really a lot of difference between the two groups. So you'd pretty much get it wrong as often as you got it right if you were trying to guess which group was which. And we can express that mathematically in terms of changes in proportions. So if you looked at someone who is average, 50% mark, they undertake an intervention that improves their score by 0.2 standard deviations, that effect size of 0.2, it would move them up 8 places in a class of 100 kids. So we're looking at fairly small changes, but feel for what an effect size might look like. Now, an effect size of 0.5 is starting to move those groups apart, and you're starting to get a bit more confident if you're making a guess. 6 times out of 10 you'd probably get it right. And it's the difference in height between 14 and 18-year-old girls. Well, assuming they're in silhouette, by the way, not using other kind of cultural factors to guess their age, just looking at their height alone, starting to think, oh, that might be a way of telling them apart. And you're starting to see a more significant jump for that average child, moving from 50th place up about 19 places in my league table. So that started to get really interesting. If you're talking to a head teacher and they were 50th ranked in their local area, and you can tell them an intervention across the school would guarantee to raise every child's score by 0.5 standard deviations, that effect size, they'd be really excited in moving nearly 20 places up the league table. So that's starting to get educationally really. And if we kind of extend that, you start to see that an effect size of 0.8, those groups, my distributions, are starting really to slide well apart. And you're starting to see that an intervention is having quite a dramatic impact at that point. And the head teacher is now getting really excited because he's moving up from the average school at 50th to nearly in the top 20. Imagine if you could tell your vice chancellors that you had some wonderful university intervention that would move your university up the league tables to that level. They'd be paying you thousands and thousands of pounds to achieve that. Why effect size is so important is that for years the concept of significance, statistical significance, has dominated whether or not research is taken seriously. And I know I'm kind of glossing some of the complications there, But in education, most educational research is beneficial. Most educational research is positive, and we want to know how big the effect is, and that's why effect size is so powerful. If you've got a piece of research and you find a nice statistically significant result and you've had a large sample, it might be a tiny, tiny difference between the two groups, which might not be particularly educationally interesting. And that's why that notion of significance is problematic, because it muddies the idea of statistically significant and educationally significant. Large effect sizes would be educationally significant, and that's why I'm particularly interested in the concept. Traditional reviews tend to focus on statistical significance. Tests for publication, you're often more likely to submit something for publication if you've got a significant or statistically significant result. But meta-analysis is trying to look at the direction and magnitude of the difference. So rather than is there a difference and is it real mathematically, to how big is the difference and how consistent is the difference. So that's the key issue I think we're trying to achieve with the concept of effect size. So meta-analysis is trying to look at quantitative data cumulatively, comparatively, but ultimately correlationally. And as I say, the metaphor of it surveying educational research is quite useful, because that's effectively what you do. You go out and collect lots of studies and you ask lots of questions about each of those studies, methodologically, in terms of the intervention, what sort of outcome measures were used, age of pupils, and you enter all of that into a database. So you can think about relationships between, do particular interventions work better with girls or boys? Do they work better with younger or older pupils? Are longer interventions better than shorter interventions? All of those sorts of issues you can draw out from a meta-analysis. I'm going to spend a little bit of time explaining one of the key ways of presenting results from meta-analysis, because I think, again, it gives you a nice visual picture of what's actually happening in a meta-analysis. They're not as consistently used in education and social science as they are in other fields like medicine. And I certainly would argue that it's pretty much essential. If you're doing meta-analysis, you should present your results in a forest plot, but it isn't yet standard practice. But it tells you a lot in providing a visual model of a meta-analysis. So this would be a typical plot that you'd see perhaps in a research article or in a research report. And it starts to give you an indication of what the data shows. And this is the interesting bit, because what it's starting to show you here is what the range of effects is and how confident you are in the precision of those findings. So you get your list of studies down the side. You'll have a study effect with a confidence interval. Confidence interval, the way I understand it, is that if you were to repeat that experiment 100 times, 95 times out of 100, your result would lie somewhere on that line. So it gives you an idea, if you like, of how confident you are of where that dot should be. And as you can see from this, that varies quite a lot, and then when we come on to sample size here, you can see that the really long line is the smallest sample. And that should start to make sense for those of you with a more quantitative background, that you would expect a small study to have less precision about your confidence in its overall effect. Line of no effect is plotted there, so that's now also starting to get interesting. We've got overall a skew towards the side that favours the intervention. The confidence intervals are represented by the line as well as by the numerical data, and the red blobs indicate the study effect size. In fact, the larger the square, the greater weight that it has in the study. I could talk for longer about weighting, but just for the moment, suspend your disbelief. And there's a strong link between the size of the study and the size of the square, is what I'll say for now. But then what happens when you combine those effects, you end up with a pooled effect size, which is shown by the black diamond at the bottom. And the points of the diamond on either side indicate the confidence interval for that pooled effect. Now that's where it starts to get interesting, because you've had these, 6 disparate studies doing a narrative review. How confident would you be to draw conclusions about whether or not this intervention's positive or not? But then when you pool the results, you come up with a much clearer answer to that question if you're convinced by the data and the process that the researchers have gone through to aggregate that data. If you look at, again, those studies where the confidence interval crosses the 0 line, that would mean that those studies hadn't reached conventional statistical significance. So we've got 4 of those 6 studies haven't reached conventional statistical significance. 2 of them have. Again, if you're doing sort of vote counting or narrative method, you may well be starting to draw conclusions that would lead you to think that this particular intervention isn't effective. Meta-analysis directs you to the opposite conclusion, that if you had been able to run all of these studies as a single study of the size of all of the participants in it, you'd be very confident that overall it was a positive effect. And that's meta-analysis's power. Now, that's the simple version of meta-analysis. Of course, there's a whole host of statistical questions behind that. And I won't today be going into some of the detail of the issues around weighting and different models for these. But there's a fair amount of that in the literature. I want to pick up a couple of issues I think I need to in terms of issues and challenges to meta-analysis. Because obviously the quality of that reduction to an overall black diamond at the bottom of the last slide depends on how conceptually comparable those studies were that were put into the pot at the beginning. And that for me is always the most important issue. The other issue that is often leveled as a criticism against a meta-analysis is that you reduced it to an answer of 42, or 0.42 would be more usual in meta-analysis, and that may simplify the complexity of those ranges of interventions in a way that isn't helpful. And that's again what you need to decide as a meta-analysis, in the same way that deciding whether or not an average is fair is an average a fair representation of that data set. And that to some extent depends on what question you're asking. If you're asking the question, overall, is this intervention beneficial, then meta-analysis is useful. If you want to know how those interventions work, then it's not the right way to answer that question. The other challenge to meta-analysis that's always thrown is that it's like comparing apples and oranges. Jean Glass had a nice rejoinder to that, which was, of course it's like comparing apples and oranges. In the study of fruit, that's the only sensible thing to do. And that's the question. Are you interested in apples or oranges, in which case you don't do a meta-analysis, you look in the depth at the studies that have been done. But if you're interested in a broader question, the study of fruit, meta-analysis is appropriate. That decision is a complex one. The other, the final sort of common criticism level at meta-analysis from a conceptual theoretical level is that it is atheoretical. It's only interested in what works, it's not interested in how or why things work. I think empirically that's simply not true. In education there have been a number of very strongly theoretically driven meta-analyses. A large one more than 10 years ago, Sipe and Collette, used meta-analysis to test Wahlberg's educational productivity model. So they collected lots of studies to look to see where effects were greatest. It was a really impressive way of testing a quite difficult theoretical model. Robert Marzano did something similar, looking at the relative levels of effectiveness of self-cognitive, metacognitive, and self-regulatory control systems. So again, he was driven by a strongly theoretical model and used meta-analysis to test that. So I don't think it is about answering the what works questions, although it can do that. There are technical issues that I need to kind of flag up. Heterogeneity would be where you had study effects that were widely scattered. And that deciding whether or not you can average those to a single effect may well be problematic. In education, a number of other domains, publication bias is very much an issue. I tend to work most in the field of technology in education. That field is characterized by enthusiasts trying out new technologies with willing participants who want to make it work. It's less likely that they'll publish their unsuccessful studies and failures. So that's one field within educational research where you're more likely to find a strong publication bias, I'd argue. I've got something I call the dissertation test. If you find PhD theses on the same topic and check whether or not the effect sizes are similar between the PhD theses and the published research, I'm relatively confident that there's not publication bias, because usually the reason for not completing a PhD isn't usually because you've got non-significant results. You find some other way of talking about them. So that's kind of my rule of thumb. But it is a problem, particularly in education research. And there's a vexed issue of methodological quality. Do you rate studies according to how well they've been done and then assign different weight according to that? I think it's an empirical question. My view is that you code for methodological quality, stick them into your meta-analysis and check to see, are your low quality studies getting much higher effect sizes, in which case you probably do need to be cautious. Are they all coming out about the same? Well, there may not be a close relationship between how well someone can research something and how well they can deliver an intervention. So the intervention effects might be genuine even though they haven't researched them well. So you might want to tease out methodological issues. I'm moving towards the end of, as I say, this fairly short presentation. What I'd like to convince you of is that it's an area that you should be taking seriously, and PhD students should be taking seriously, even if they're not undertaking quantitative research. I think that meta-analyses form part of the evidence base in most fields, and this is a graph showing the increase in the number of publications, the absolute number and percentages. Absolute numbers on the right-hand side, percentages down the left, and it looks like an exponential curve. I mean, it can't be. It presumably will flatten out. The other thing I'd also comment, for those of you who are slightly more cynically and citation-minded, is that meta-analyses get a very high number of citations. So if that's a direction you feel you need to go in for your research, then reviews and particularly meta-analyses get widely cited. My concern at the moment is that the large number of people within social sciences and particularly education haven't had training which has included meta-analysis. Partly, I think, simply because packages like SPSS can't do it, so it's not part of the standard training in social sciences. But that means critiquing meta-analyses is problematic, and there's definitely a skills gap in being able to understand a meta-analysis well enough to know how and where to critique. So that, I think, would be my key issue. And then just to whet your appetite, some findings from meta-analysis. Now, this probably shows more about my research interests than anything else. They're very technology focused. But Bernard's study in 2004 compared distance education with classroom instruction. A chunky number of studies, 232 studies with an even larger number of effects. But the effects were really widely distributed. I'm a bit skeptical that you could really combine those into a single overall pooled effect size at the end, because the pattern of results is so distributed. But one thing that comes through from that caught my attention was that asynchronous distance education, so that's when you're not online at the same time, is more effective than synchronous. And if you think of the way that we're being pushed in universities to provide synchronous online teaching and communication, either through being online and email or through video, the evidence suggests we should be a bit cautious about jumping to that as a conclusion in terms of effectiveness. Now, it may stand as a proxy for motivation. It may be that those who are committed to asynchronous courses are the ones who are going to persevere anyway, and the ones who go for courses that have synchronous and think it's going to be easier. So there may be all kinds of variables that's hiding, but I think that's an interesting finding that we should be aware of. Pearson's research on reading comprehension and digital tools suggests that technology has a beneficial effect on reading comprehension. My reservation there is I can't see a clear causal mechanism that links the different articles, other than perhaps at a general motivational level. So although there appears to be a consistent finding, the studies seem to think it's the technology, and I just don't buy that as an answer. The technology itself doesn't strike me as being likely to have that causal effect. Clower and Fye's work is interesting for those of you who are interested in transfer. Their thinking skills program is very cognitively focused, training in inductive reasoning, quite a narrow field, and yet they get a more impressive performance on general schoolwork and school tests than they do on intelligence test performance. So that seems to be implying a transfer effect to general academic work. For me, that sets I need to know more about that, is sort of my reaction to that. And then the final one I've picked out is a very recent one, Gersten's review of math interventions for low attainers. Much more modest range of effect sizes overall. They didn't combine them because you can see the range there, 0.21 to 1.56. That's the distributions are nearly entirely separate at that point. I'm having trouble believing that one myself. I kind of need to go back to that original study. But they didn't combine them into a single overall effect size because they didn't think that was a fair way to represent the data. But what came out of that was teaching fairly simple heuristics, and direct instruction was beneficial. On the presentation, you'll find some suggestions for further reading and some websites. If you're interested in things like software, I particularly recommend the University of Murcia's website. They keep their site up to date far more quickly than I do mine, and are much more up to date with what's available. Sorry, it's not terribly legible for those of you at the back, but the presentation's on the web. Okay, thank you very much.